Cool. So I'm Abhishek, co-founder here at TrueFoundry. At TrueFoundry, we are basically a platform that helps companies build and deploy machine learning applications, models, and then even provides an LLM gateway to talk to different models and all. Today, what I'll be talking about is one of the major problems that we faced, and I'm sure a lot of you guys will also face in your own company. So what we have is, as part of TrueFoundry, we help our customers deploy these models on GPUs and everything, and as part of that, we also need to do a lot of testing. Like for example, if we want to deploy Llama on 8 and GPU, so what is the most optimal configuration, all of that. Now the problem with this is like a lot of our developers need to start up GPUs, quickly test their service, and then probably shut it down over the weekend, right? Like you're not testing it constantly, at least in the dev environments. Now imagine we have 20 developers, each of them wants to start a GPU, 2 of them forget to turn off a GPU. There's a huge massive cost of drain that we incur. Like because of developer errors, you run into problems where we start draining a lot of cloud cost. And that was one of the major problems that we were facing. The second problem that we had was, and I'm not sure like how many of you do it in your companies, but for us, every single pull request gets deployed as a whole staging environment. The advantage of that is I can test out my entire software end to end with every single PR that I raise. Does this happen in any of your current companies? Just curious. Yeah, so we have a few people who currently do that. The advantage of that is we really accelerate developer productivity a lot. Every single PR becomes a full entire system. You can test it, confirm it, and then close out the PR. The problem with that is we have almost 50 pull requests open at any point of time. That means 50 copies of the system are deployed parallelly at any point of time. This costs us a lot. Like 50 pull requests open, but you only want to test the system when you actually just want to test it. The rest of the time, the system doesn't need to be up. Now, a pull request can remain open for, let's say, 2 days, 1 day, something like that. So for 1 day, I'm actually paying the entire cost of that infrastructure when I could have just kept it alive for like 20 minutes when the developer is testing. So these are like a few, at least the 2 problems that we encountered, but I'm sure you'll have cases where you want to start up something, quickly test it out, and then it should automatically shut down. A lot of cases like we have to remember to shut it down, and many people will remember, some will forget. I usually don't remember a lot of things very, very rigorously. I tend to forget a lot of things, and somehow we have a few developers in our company who also are like me. The problem was we could have said that this problem is like you are the fault, you have to shut it down and things like that. We decided to take a different approach, that how can we make the systems that smart that it automatically shuts things down. So just to give you an impact of what we actually faced, we actually left on 1 GPU machine on for just a month. Nobody realized it, and that testing was done only for 2 hours. For 1 month the GPU ran, we blew up like it was a 4 GPUs in one machine. 1 GPU cost $2.85 an hour. We ended up doing like $10 an hour because there were 4 GPUs in one box, and we ended up at the end of the month we saw $10,000 of cost in cloud cost, which was absolutely a waste. And this was just one instance. We had multiple instances like that, and we knew that this is a waste. Like we could highly reduce this. Like my actual testing time, if you take 2 hours, I would have spent like $20. Instead of $20, I ended up spending like $10,000. The same thing happens in our PR environments. Our whole software takes up around 20-25 CPUs. We actually keep it running for the entire 1 day or 2 day the PR is open. So this was the problem that we wanted to solve. Now, let's say if I start solving this problem, what do I have to do? Like I have to figure out when the developer is testing, and the moment he's done testing, I need to shut down the system. Now, how do you enable this? And we are operating on Kubernetes and things like that. Any ideas anybody has, like how would you do this? Like GPU should shut down when the developer is done testing with it. Any ideas? Do any of you face such a problem in your company? Just curious. So you do? So yeah. So we have a few people who do face this problem. This problem will happen if you're operating, if you're like doing very, very rapid development or dealing with GPUs and things like that. That's when you encounter this problem. So what we decided was we looked around what is available, how we can solve this problem. And there were a couple of solutions that we found. One is Knative and one is Kda. In Knative, what you can do is you can say that only when a request is coming, my server will start up, and when the request stop, like there's no request for the next 10 minutes, my server will automatically shut down. This is something you can enable in Knative. The problem is in Knative, I have to rewrite all my deployment manifests according to Knative. Like I can't do my standard because Knative comes with its own custom resource, and we don't want to do that because in our production we don't want Knative. In production it needs to run, the GPUs need to run constantly and everything. So in my dev I have to use Knative, in my production I don't want to use Knative. It's a overkill to use Knative in production. So that is not an acceptable solution because then I have to change my whole deployment stack between dev and prod, which is not a great option for us. And also Knative is a bit complicated rather than just doing a simple deployment spec. So it comes with its own installation and all of that. The second option we had was KDA. Have you guys used Knative, anyone here? Okay, nice. And KDA? Awesome. So in KDA there is a thing called KDA HTTP on adapter, using which you can do scale to 0. The problem with that is your HTTP KDA, the way it achieves that scale to 0 is by putting a proxy pod before your application pod. So the traffic first hits the proxy, then goes to your application. We didn't want this to be always true because we are doing a bunch of latency benchmarking and all, and we don't want the KDA pod to be the single point of failure. We want to send traffic directly from our client to the service. So this was the two reasons. Like we really spent a lot of time trying to use these two systems, but they were causing a bit of like friction, not meeting our ideal requirements. That's when we actually took down the path. We took inspiration from both the systems, Knative and KDA, and we built a system called kubelasty. Kubelasty is a system that basically combines the best of both worlds, both Knative and KDA, and offers a scale to 0 solution on Kubernetes. The way it works is it doesn't come in your critical path. It only comes in the critical path at the start of the request and then removes itself from the critical path. So I'll now hand it over to my colleague, Shubham, who is basically the primary engineer who actually devised this entire solution, and he will walk you through it.
Sure.
You can take this.
Hello? Okay, this is not good. Hello? It's green. Hello?
Yeah.
Okay. Okay, I'll have to actually operate from here because I have to run a few videos. So the requirements were pretty clear. You need something that has universal workload support. So it should be able to scale anything that supports a /scale sub-resource, if you guys are familiar with it. So anything that is a deployment, a stateful set, an Argo rollout. We had to use Argo rollout in our production. So we wanted to scale that. We wanted something that would give us 0 downtime. So basically no request can be dropped. If a request comes in, we just scale up just in time, and then the traffic needs to go to it. We cannot allow any request to be dropped. And then we wanted something which was truly non-intrusive. So it should work with standard Kubernetes manifest. So as Abhishek said, with Knative, this is the problem that we had. We did not want to move away too much from what standard Kubernetes manifest already provided. So, okay, yeah, this is loaded. So this is an animation which basically shows you what are the different components in kubelasty and how a request flows, how a workload is scaled up, and then how it is scaled back down. So I'll just play this, and I'll pause it in between so that we can see the different stages. How did this happen? It was just working. Okay, let me try this again. This works. Okay. So what I'll do is I'll just slow this down a bit so that we can actually observe the different things. So okay, so the starting state is we have a pod available over here, and it is scaled up. Traffic is directly routed from request ingress service to the final pod. And then we have Prometheus sitting over here, and there are two components in Elasty. There's the Elasty controller and Elasty proxy. Elasty controller, what it does is it continuously polls Prometheus, and it takes a decision whether to scale the pod down or not, which we'll see. So Elasty controller is continuing to poll Prometheus. Now, okay. Yeah, so as you can see, like it is starting to scale down to 0, and there are 0 pods now. Another thing to observe is the service is now directly pointed to Elasty proxy, and Elasty controller has just scaled this workload down to 0. So we are not incurring any cost now. Now going to the next stage, Let's wait for a request to come in. So you can see this blue dot. This is the request coming into the system. And let's wait for it to hit service. Okay, let me speed this up a bit. So it hits the service. And since service is now pointed to the Elastic proxy, it goes to the Elastic proxy. And yeah, as soon as it hits Elastic proxy informs Elastic controller that we need to scale it back from 0. So the pods are going to get scaled up. The request is still held in Elastic proxy. The pod is now scaled up, and the request will now be forwarded to the final pod. Right. So as you can see, the request is being forwarded to the final pod. Another thing to see is this line is now dotted, which means that the service is no longer pointed to Elastic proxy. And dynamically, now there's a new request that has come into the system, and this will now directly flow to the pod without going through Elastic proxy. So this is how we solved the problem that we were facing with KEDA HTTP add-on, which was a proxy that would continue to be in your critical path. So yeah, I mean, the traffic just flows through to the final pod, and that's it. This is a small demo for it, just to show how easy it is to set the tool up.
I have a Kubernetes cluster.
Is this audio being recorded?
With
No, right.
gateway installed.
Okay, if the audio is
Any gateway.
audible.
Prometheus installed and a service which I want to scale up and down.
You can
Let's
put the
start
mic.
by install it. You can just copy the command from here, connect to your cluster and just install it. Since the service is scaled down to 0 right now, any request I send to it should immediately fail. Let's try it out. No healthy upstreams found. Now that Elastic is installed, we can go to the second step. We can skip the verification. So we need to create a Elastic service CRD, which basically tells Kube Elastic which service to monitor, which service to scale down after a certain period of time. I have already created a dummy Kube Elastic service for this example. So I'm targeting HTTP build service. I want minimum replicas 5. So when it scales up, it should reach minimum replica of 5. Cooldown period in seconds is how much time to wait before to scale down a service in case of no traffic. This is the deployment which we are targeting and which we need to scale up or down. This is very interesting. So triggers is what tells Kube Elastic which service can be scaled down. In this case, we just provide the query, the address of Prometheus, and the threshold below which, if it is, we can scale down. So I'll just apply this file. Yeah, that's it. The file is applied, which means that now this service HTTP bin is under Elastic. And unlike the last time where the request failed to it, this time the request will go on hold. The service will start to scale up. The moment one replica comes up, the request will fulfill, and slowly all the requests would start coming up. And that's how easy it is to set up Kube Elastic. There's no infrastructure changes are made. And yeah, that's it. That's the magic of Kube Elastic.
Right. So as you saw, like it's just a CRD that has to be applied along with deployment and service, and that just does the service proxying part. So this is a sample configuration. In this case, what we are doing is like min replicas 0, max replicas 1. So the maximum replicas that, sorry, I mean this is a little bit incorrect. The idle timeout second is what is actually important here, 300. So in the case that Abhishek mentioned earlier, we have the ML engineer deploying the GPU-based service. And in this case, what happens is while the GPU-based service is actually in use, it remains up, but and then it gets scaled down in step number 3 after 300 seconds of inactivity. The other thing that happens is like if the developer comes back and tries to use the service again, it is brought back again. Same for the front-end preview system that Abhishek talked about. So every new PR gets its own complete deployment and service setup created along with Elastic service. So all of them are scaled down by default, so you're not incurring any cost. But as soon as a PR reviewer comes in, clicks the link, and the PR itself, the environment behind the PR gets scaled up, and you are able to see the front end and basically review it. As soon as the review gets completed, it gets scaled down. So through this, like, we are able to maintain a lot of different PRs with their own links, which are always available if someone needs to review them and so on. So there are some constraints to the system, some limitations, so to say. One is that if your workload has a very high cold start time, so let's say a GPU workload, which is very, I mean, you don't know if you are even going to be able to provision it or not, then in that case, there is a chance that the first request ends up timing out. Although the request, although the pod and so on, the node will end up getting provisioned. But yeah, there is a chance for timeout initially. For non-standard traffic flow, for basically anything that bypasses the service object within Kubernetes, this does not work right now. So basically, a setup like an application load balancer, which directly points to a pod IP in case of AWS. So in that case, like, this is not going to work. Then there is load balancer health check. So if a load balancer is continuously giving health check, that will keep the pods up, because Elasti is looking at a request without actually looking at what is there underneath. There are other limitations around metrics ingestion. So basically, we support Prometheus as the metrics source right now. But yeah, we are planning to increase that. And on-prem infrastructure, so if your infra itself is not flexible, you're not going to get anything out of it, because ultimately what you're paying for is the allocated resources. So with that, I'll just conclude this. So we have our roadmap, which is basically like we are integrating more Prometheus, more metrics, triggers, and so on, different workload supports. It is completely in the open source and now donated to CNCF. So you can go and look at it under github.com/kubelasti/kubelasti or kubelasti.dev. And we have our Discord community, so feel free to just join and chime in if you want to contribute, or if there are bugs that you would want us to look at. Thank you.